In modules 2 through 5, we built linear chains, one monomer at a time. Now we add a third dimension. When a monomer can react 3 or more times, chains can branch. And once branching is intense enough, something dramatic happens. The whole system locks together into a single giant molecule. We call that gelation. Bifunctional monomers can only string together into linear chains. A trifunctional monomer with 3 reactive groups can branch. 1 branch becomes 2, 2 becomes 4, 4 becomes thousands. If enough trifunctional monomers are present, the branches eventually link up. At a critical extent of reaction, one connected molecule spans the entire reactor. The mixture turns from a liquid into a solid. This is the gel. There is a sharp transition point called the gel point. Below it, every molecule has a finite size. The system is a sol. It flows. It dissolves. Above it, one molecule is infinite. The system is now a gel. It does not flow. It swells, but does not dissolve. The gel point is a phase-like transition. Pourable liquid below, jello-like solid above. Tiny change in conversion, enormous change in properties. 2 predictions for the gel point. Carruthers' theory uses the average functionality of the monomers. Its prediction is 2 divided by F average. Flory-Stockmayer theory takes more detail into account, including stoichiometric imbalance R and the branching fraction ρ. Its prediction is 1 over the square root of R times 1 plus ρ. The 2 predictions usually differ by a few percent. Flory-Stockmayer is more accurate when branching is uneven or stoichiometry is off. Here is the cleanest signature of gelation. As conversion approaches the gel point, the average degree of polymerization diverges. It blows up. But if you exclude the largest single molecule, the average stays finite. That is the gel forming. One molecule is swallowing everyone else. The largest cluster goes from a few percent of the mass to nearly the entire system in a very narrow window of conversion. Let us compare 2 systems, both made from A-AA-A3 and B-BB. First, low branching, with a 5% excess of B. A3 over A-AA is 0.1. A to B is 0.95. Predict weak gelation, because the B excess starves the network. Second, higher branching with perfect stoichiometry. A 3 over A-AA is 0.5. A to B is 1.0. Predict sharp, clear gelation. Open the Module 6 notebook. N equals 5. A3 over A-AA is 0.1. A to B is 0.95. Run all. The largest cluster grows slowly. Mean dP stays bounded. Sol fraction stays high. The system barely gels. Now raise the branching and fix stoichiometry. A 3 over A-AA to 0.5. A to B to 1. Run all. The mean degree of polymerization spikes dramatically. The Sol fraction collapses toward 0. The 3-dimensional network plot fills the box. This is a clear gel. Same chemistry, 2 knobs turned, 2 completely different end states. 2 takeaways. Branching enables gelation, but stoichiometry decides whether you ever reach it. A small excess of one functional group can stop a network from ever forming. For instructors, this module is a perfect predict then verify exercise. Compute the Carruthers and Flory-Stockmayer gel point first, then run the simulation. For students, sweep a 3 over A-AA from 0.1 to 2, and watch the Sol gel boundary shift.